Okay, good afternoon everyone. Let's get started. Happy Halloween. We prepared this demo for you to play with. You can generate any images. So for example, here is generating Halloween pumpkin. This is using the hybrid autoregressive model we developed. We are going to talk about that in the later part of this lecture. It's super fast. It's running on A6000 GPU in the basement. Just take a few seconds to generate new images. The website is heart.mit.edu, so feel free to play with it. Okay, so today we are going to talk about lecture 16. Let me start the slide. Okay, welcome to lecture 16 about vision transformers. So we learned about using transformers for language modeling, okay, for such as large language models, lots of NLP tasks. But the transformers is so powerful that we can also use the same architecture to model the images, to extract the features for images. So this is the agenda for today's lecture. We're going to first talk about the basics of vision transformer, and then talk about how to accelerate that, because vision transformers are basically super big. How do we make it faster? Using windowed attention, using linear attention, such as EfficientML.ai, and also using sparse attention to accelerate these vision transformers. Next, we are going to talk about self-supervised learning for vision transformers, how to continue to scale it up without having to have access to many labeled data, using contrastive learning, using masked image modeling. And finally, we'll talk about VIT with autoregressive image generation. In particular, we'll talk about the techniques behind the model, behind the demo I just shown, the hybrid autoregressive transformer done by our TA Hao Tian. So let's start with the basics of vision transformers. So remember, in transformers, what is the basic building block? So the input, the granularity of the input is tokens, right? So text is very easy to be converted into tokens. Each word is roughly a token, right? Some words are 2 tokens. But how do we represent images with tokens? How can we tokenize images? A natural way is actually to convert the image into patches. Like in this case, we have an image, and we divide it into 3 by 3, 9 patches. Here are the 9 patches. So we convert the 2D image into a sequence of patches. Okay, and we consider each patch as a token. Okay, so for example, in the original image, the dimension is 96 by 96, and the patch size is 32 by 32. So right here we have 9 tokens. Okay, so we have 9 tokens. The dimension of each token is 3 by 32 by 32. Okay, so roughly 3K. And then we do a linear projection. To flatten the patches. The patch is 2D. We flatten it into 1D. Okay, and we project it from roughly 3K to 700, 766 to 68 in this case. Okay. So we convert 2D image into a sequence of patches using this way. What is the practical implementation of that? So rather than using an FC layer to project between 3072 to 768, we can just use a convolution, right? Use a convolution. The kernel size is 32 by 32. That's the dimension for each patch, 32 by 32. And the stride of 32 as well. And padding to be 0. In channel is 3. Since input we have 3 input channels, RGB. And the output channel is 768 for the output channel. And then we can apply the standard transformer architecture after applying the positional encodings, right? Otherwise, we don't know where the pixel come from, so we need to apply the positional encodings. And then we can feed the patch embeddings to a standard transformer encoder, just like language. And there are several variants of the vision transformers. For example, there is VIT base, VIT large, VIT huge. They have different layers. VIT large has 24 layers, hidden dimension size is 1K, NLP 16 has roughly 300 million parameters. And usually there is another notation, /16. That means the patch size is 16 by 16. Okay, so you can have different patch size. The larger the patch size, the more coarse the granularity is. So how does VIT compare with CNNs? Okay, so this is showing the number of training samples. The y-axis is top line accuracy. We are comparing the VIT and CNN when the training data is not a lot. Not a lot. Actually, VIT is inferior compared with CNN. However, when we have a lot of training data, okay, so VIT actually surpass CNNs when the pre-training with a very large data set. So VIT scales better than CNNs. But when the data is small, CNN is more efficient. Okay, so having introduced the basics about VIT, let's talk about how to make it more efficient, how to make it tiny. We are going to introduce the efficient VIT techniques. Before that, let's first introduce why it's crucial to let VIT handle these high resolution images. Okay, for example, medical image segmentation, we need to have those fine-grained details. For example, this is diagnosing kidney size. We need very fine-grained resolution. Lots of tasks require this high resolution, dense prediction, such as super resolution. This is low resolution, this is high resolution. We can accelerate it to make it much faster, 41 frames per second compared with 16 frames per second. Such super resolution task is widely used. For example, in NVIDIA DLSS, basically it's doing the super resolution, given a low resolution video, make it high resolution, and that require real-time processing. And also, high resolution is important for autonomous driving tasks. So if you are using a very low resolution, like in this image, you can hardly distinguish there's somebody riding a bike right here. But right here, given a high resolution image, you can tell actually there is a people riding a bike or a motorcycle right here. The accuracy actually grows with the resolution. Right? So here we are comparing the IMIOU, which is a bunch, which is measuring the quality of the segmentation task. The high resolution, the red bar, compared with the low resolution, the gray bar. Actually, there's a big gap. There's a big improvement from low resolution to high resolution. However, increasing the resolution, there's no free lunch. You see the max, the Gmax computation for VIT is actually grows much faster compared with the CNNs. Right? From 1K to 2K, the computation for VIT grows much faster. Why is that the case? Think about the attention mechanism. It's O(n) squared, right? N is the number of tokens. The number of MAC is O(n) squared. You need to calculate token by the attention between each token. So the computation complexity is O(n) squared. And the number of token is equal to the resolution to the power of 2, right? So therefore, its total computation is resolution to the power of 4. So it's pretty computing intensive. So how do we solve this problem? Actually, efficient VIT can make it much faster. This is compared with the baseline, which is running 1.6 frames per second. Transformer is very pioneering work using transformer for segmentation tasks. At that time, the frames was pretty low, but after the acceleration, we can find efficient VIT can make it much faster, from 1 frames to 21 frames per second, but still while maintaining the accuracy. So this is measured on a NVIDIA Jetson Orin, a driving GPU, driving mobile GPU, in FP16 batch size 1. And high resolution dense prediction is also helpful for these AR and VR applications. Like there is a dog indicating where you are looking at, and it's going to tell to segment the stuff you are looking at. And that is using this paper called segment anything. Basically, the image is passed through an image encoder, which is a VIT. This is taking the majority of the time and get an embedding. And then the prompt could be a point, could be a box, could be a mask. You encode the prompt and then mingle the image encoding with the mask and finally predict the final mask. So such work require pretty heavy image encoder based on VIT. And then you can take mask as input prompt, point as input prompt, or box as input prompt, or even text, which is not released in this paper. So it's promptable image segmentation. And it is an ambiguity-aware design. Like you can segment the entire scissors, or only the handle, or only one of the handles. It has an automatic data engine to use this model to annotate more data and use more data to train the model. Okay, so those are some of the use cases about dense prediction. And the use case of VIT as the image encoder can do a lot of applications. So given those motivations, let's see what are the right ideas to accelerate and make it more efficient to deal with the VITs, starting with the window attention. So previously, we are converting the patches across the whole image. So every patch in the image can attend to each other. So if the image resolution gets pretty large, the computation grows quadratically. So instead of doing attention computation over all the tokens, we can apply window attention. Okay, so the attention mechanism only happens within the window. Okay, so say this window size is 7 by 7, so the attention only happens within this local window. Okay, since the number of tokens in each window is fixed, the computation complexity is linear rather than quadratic in this case. For example, here, each patch is 7 by 7, and we do the attention within the patch, and we have many patches right here. So this is the original attention where each patch has to attend to each patch. Now we can divide it into several windows, and only the tokens within the window will attend to each other. So what is the problem of this case? Tokens only attend to each other within that within that window, right? So adjacent windows, the tokens cannot attend to each other. So the information cannot flow. So that's the problem. So how do we solve that locality problem to enable this kind of global, much larger receptive field? So actually, a shift operation is added to this window attention. Okay, not sure. So for the layer 1, okay, this is the window divided by 2 by 2 windows. And layer 2, we actually shift the window. We can shift this window by 2 boxes, okay, so that adjacent windows, the tokens in the second window can also attend to the first window, okay, in the second layer. So if we repeat this process, all the tokens will be able to attend to all the tokens, no matter if they are in the same window or not, thanks to this shift operation. Okay, as a result, this method actually achieves better ImageNet accuracy than the VIT. So these are VIT top-line accuracy. This is the swing transformers, shifted window attention, swing transformer accuracy, better than the original VIT. Not only on ImageNet, but also on other tasks like object detection and also image segmentation tasks. So are all the windows useful? Actually, it's not the case. Sometimes sparsity can also help. Not all the windows are useful. We can safely discard a lot of windows, especially in point cloud. Actually, 99.9% of the voxels are actually sparse. There is no object, like right here, there's no object. So the spatial sparsity is pretty high. So how do we exploit those sparsity? We can use window attention. The white area shows there's no point, so it's 0. But how do we divide the window, right? How do we set the window? So one way is to apply this equal window grouping, an equal window. Like this is a window, C itself, AE is a window, HBG, this is a window. It's very regular, it's 2 by 2. Okay. However, if we do it in this way, the window size is highly unbalanced. Like the purple window has only 1 element, the next one has 2 elements, the red one has 3 elements. So this leads to difficulty for parallelism, right? So the slow one need to wait for this fast one. Okay. Another way is actually to apply equal size grouping rather than this equal window grouping. So group based on the number of elements such that for each group we have exactly the same, very balanced distribution about the number of non-zero elements. Okay. So we group the first 3 elements in the first window, the next 3 in the second window, the next 3 in the third window. Actually, that's perfectly balanced. And as a result, you can imagine this is much more hardware friendly and can run much faster compared with different transformer-based models, and even faster than convolution-based models. This is convolution-based model, and this is a transformer-based model measured on a NVIDIA Jetson Orin driving chip. Okay, so this is using window attention and sparse window attention. Since the attention mechanism has open square complexity, a natural optimization is, can we simplify that to linear complexity? Okay, so that they use this linear attention. Okay, so let's switch here to linear attention. Before that, let's first see the softmax attention equation. Okay, so we have QKV. We first QK transpose. We get an n by n attention mask. This is O n square. Scale it by square root of d. Find the softmax and use that to do the weighted sum with the v to get the final output. Okay, so the cost is O n square. Primarily do it here. This is a slightly changed version. Okay, so using ReLU linear attention. So we first do the Q and K. We pass the ReLU activation function right here. We pass it through the math-mod, scale it, and then finally multiply that with v. So the cost is still O n squared in that case. So can we change the order such that we can have O n rather than O n squared complexity? Okay. So that reduces the third solution. Since AB times C equal to A times BC, okay, so this is the associative property of the math-mod operation. Okay, so rather than QK first, we do the KV first. Okay, we do the KV first, so it's D by N, N by D. So it's O N D square. Okay, N D square is proportional to N rather than O N square. Right? So it's O N D square. And then we multiply with Q in the last order. So by changing the order, it becomes switches from O D N square to O N D square. Okay, so it's proportional, linearly proportional to N rather than to O N square. So we change the order of the math-mod using such associative property, and we can reduce the computation complexity. Does this work? Actually not, right? You can imagine reducing the computation, there's no free lunch. Originally, using the softmax attention, the attention is very strong at the points of interest, like the eyes of the dog, the nose of the cat. It's very strong attention. But using linear attention, everything becomes pretty weak. The eyes is no longer red, and the cat, the nose is no longer heavily attended. It becomes very flat. If you plot it, it's indeed the case, such as using the softmax versus without using the softmax attention, the blue curve becomes much flatter compared with the red, which shows that the ReLU linear attention cannot produce the sharp distributions. Okay, so it's good at capturing global context information, but not good at capturing those local information. Right? Like this local information is not captured in the linear attention. and also lacks this multi-scale learning ability. So how do we deal with that? As a result, we can see there's a big accuracy gap if we replace the softmax attention with the value linear attention. The top accuracy dropped a lot. So how do we alleviate such limitation without losing efficiency, but can effectively handle the local information extraction? So let's brainstorm what is good at extracting local information to compensate for the loss of local information extraction capability. That's convolution, right? Convolution is our friend to extract local information. So we can simply add a convolution branch to do the local feature extraction without. But in order to not to lose efficiency, we use a depth-wise convolution followed by a one-by-one group convolution to save the computation right here, rather than using the full convolution. We decouple the spatial modeling versus channel modeling. So we can enhance linear attention by such multi-scale education with the convolution. Okay? So here, the FFN layer, we added the steps-wise convolution to compensate for the loss of accuracy. It added very little computation, but accuracy-wise, it fully brought back the accuracy and also actually improved the accuracy a bit. So added the depth-wise convolution can further enhance the linear attention's local information extraction capability. And as a result, we can see the speed up right here. This is on a mobile chip, Qualcomm Snapdragon mobile chip. It achieved about 5.8 times speed up with even higher accuracy on segmentation tasks. In the middle is on Orin, NVIDIA Jetson Orin for driving applications. So it achieved about 2.8 times speed up. On the right-hand side is on the cloud GPU, which is A100, achieved about 1.7x speed up with higher accuracy. Not only on segmentation, but also on super resolution tasks. So here is on two data sets. One is the FFHQ data set, which is human face data set. We are trying to do the super resolution from 512 to 1K, okay? From 512 to 1K. This is the original PSNR, the higher the better. We can achieve even higher PSNR. Originally it takes 92 milliseconds, now it's only 70 milliseconds, so 5 times faster. If we see the details, this is the bicubic, which is not quite good. This is Stormer, about 3.6 images per second. And this swing IR, about 4.7 images per second. And this is ours, EfficientML.ai, 17 images per second. And similarly for another data set, driving data set, the PSNR is a bit higher. Originally it's 50 milliseconds, now it's 2.8 milliseconds. And let's see how does that apply to the segment anything task. So here we are using the box prompt. And this is segmentation result, very good quality, but the throughput is increased from 11 to 182 images per second. So segmenting the task, segmenting the fruit, segmenting a very thin pole right here. It's very thin, but it's very well segmented for this pole. Another example is showing the dot prompt. You have a single asterisk, this is the prompt. Segmenting the pumpkin, this is a chair, this is segmenting the person, segmenting the car, right here. We can also segment everything. Right? So given a lot of dots everywhere in the image and trying to segment everything. This is before acceleration, this is after acceleration. You can see the quality is very well maintained. And this is the image classification result. This is the latency, the lower the better. This is the accuracy, the higher the better. So ideally we want something right here. So this is comparing with level baselines. This is accuracy, latency trade-off. This is the throughput accuracy trade-off. We want a high throughput and high accuracy. So why do we measure latency on Ori and throughput on A100? Because this is an edge device, usually serving a single user, like a single driver, while this is a cloud device, it simultaneously serves multiple users. Therefore, we care about throughput on the cloud, and we care about latency on the edge. Okay, so having talked about linear attention, let's further use sparsity to accelerate and simplify these vision transformers. So this is the driving scenario in Boston, the seaport area of Boston. There's a question about the resolution, right? Since the computation complexity grows quadratically with the resolution, a natural question is, can we use a lower resolution? Okay, so we can resize the image by using a lower resolution, like half of the resolution, but using dense pixel, 100% density. You can see it's very low resolution. Some details are lost. You can hardly tell this is a person anymore. So how about we use sparse but high resolution images? So high resolution is 1x the resolution, but sparse pixels, 25%. Because the total activation size will be the same in this scenario. Quadratic growth with the resolution, so here we have 25% sparsity. Which one is better? So the first step about sparse VIT, which is sparse vision transformer, is to apply this windowed activation pruning, okay, with non-uniform sparsity. So we prune away those redundant regions and only keep these useful areas, like the person here, the cars right here, which is the point of the important windows. And how do we determine the importance of the window? We can just look at the L2 activation magnitude. The activation is magnitude of that window. The larger, the more important we think it is. Okay, and then we can sort and gather by the importance, most important, second important, third important, and so on. And this is just one layer, and the second layer, the third layer, we can make it getting sparser and sparser. Okay? But how sparse should we allocate the computation to each layer? We need to search for that. So as the model is originally trained with only dense activations, so we want to gradually improve the sparsity awareness. So we need to fine-tune the model given such sparsity. So here we are doing the randomly sampling different sparsity. The first layer is always dense. Second layer gets sparser. Third layer gets even sparser. We can also sample a different sparsity schedule. So for each training iteration, we are sampling a different sparsity pattern. But what is common here is that the later layer is always more sparse than the first layer. Since if a token is pruned, it cannot recover in this case. And finally, how do we select the correct sparsity for each layer? We use this evolutionary search. Okay? Evolutionary search. We have implemented that in the neural architecture search chapter. So given we first check whether it satisfies the latency budget. If yes, we keep it. Otherwise, we resample it. So this is showing the across different search epochs. This is the accuracy. The evolutionary search keep getting better versus the random search pretty much stays the same without improvement. So now let's see how much we can improve. So here is the latency, the lower the better. Here is the MAP, the higher the better. So here we are comparing with several baselines. For example, this is under 256 resolution, this is under 224 resolution. So sparse VIT can be 1.5 times faster compared with the baseline without using sparse VIT in this case. So this is for 3D object detection, so this is for 2D instance segmentation. And let's visualize what is the sparsity mask. What kind of mask did we learn in this case? So given these are 3 frames in a driving scenario, in sparsity IT try to prune those irrelevant background. For example, this is the 24 millisecond layer model. They focus on those foreground rather than the background. The even faster, even smaller model focus on the person, the car here, the blocker here, rather than the background is all dark. Only the car is bright. So it's pruning away those irrelevant background windows and retaining those informative foreground windows. Okay. This idea might also be helpful for visual language models, which we can discard those areas that is not interesting, both in the spatial dimension and also in the temporal dimension. Okay, so let's take a break, and then we are going to jump into self-supervised learning. Self-supervised learning for vision transformers. So the motivation is that labeling the data set is pretty expensive, right? But this VIT is helpful when we have a lot of data. But such a large amount of data is difficult to acquire. So how do we train the model without needing to label the data? So we want to train with unlabeled data to mitigate this issue, right? So how do we, given a target task, okay, so how do we use unlabeled data? So we are going to talk about 2 techniques. One is using contrastive learning, the other is using masked image modeling. Okay, so contrastive learning basically consists of positive samples and also negative samples. Giving a cat, we're going to give 2 views of the same cat. Okay, so this is one view, this is another view. They are both cats, so we tell those are positive samples. And then we have a negative sample, which is a dog. Okay, so both the cats pass through an image encoder and then get an embedding. The embedding from the cats should be similar with each other. So we are going to apply the loss to pull together the features from the cats and pull apart the features between the cat and the dog. Okay. So as a result, so with random init, we can see on the Sci-Fi 10, as the model gets larger, it doesn't help. The accuracy gets even lower. But with self-supervised learning in this way, when we are increasing the model capacity from VIT base to VIT huge, it delivers stronger performance. And it's actually, the self-supervised VIT actually delivers stronger performance than the supervised counterpart. And the accuracy increases when using a larger VIT model. We can also apply multi-model contrastive learning. Okay, multi-model means here we can learn between the text and also the image. So famous work is CLIP, contrastive language image pre-training. So during the training time, we have a piece of language and we have an image. Now we pass the language into a text encoder and get an embedding. And also we pass it through the image encoder and get an image embedding. Okay? And then actually different images and different texts, they can have a attention map. So the image corresponding to the text description, okay? The image corresponding to the text description, which is in the diagonal position, will receive a high attention score. So by using such paired image text samples, we can try to supervise it by maximizing the diagonal part, which can effectively align the image and text into the same space. So at the inference time, we pass the image into a image encoder, and then at inference time can be there could be different vocabularies, and then we select the one that gives the highest attention score, which is showing that this text will align best with this image in this case dog, will align best with this image. So this is showing the accuracy of, this is zero-shot clip, this is linear probing for clip. Linear probing means just adding an FC layer to do the classification. You can see it actually enables zero-shot. So this is number of labeled training examples per class. Given zero new class label, it can give very decent accuracy of prediction versus the conventional method require at least some amount of training data, but it's pretty amazing. Clip can enable zero-shot capability. And the next technique is mask autoencoder, okay, which borrows the idea from BERT, from language modeling. Okay, so we can mask away some of the pixels in the image. Okay, we pass in remaining patches into an encoder, and then we pass it through a decoder and try to recover the original image. So this is target, this is input, which is masked. We try to predict the missing patches based on the seen patches, which reminded us about the masked language models, MLM, which we talked about in the previous lectures. So here we are masking some of the token here. The movie is very boring. We mask away boring. We pass the remaining words into the language model, the transformer, and then we try to supervise it by predicting the mask token. Okay, so we can mask a certain percentage of the input tokens at random and predict those mask tokens. And can we use a similar pre-training strategy in the region domain? So in that way, we don't have to label the images. We try to just predict the missing patches, which is coming for free. Actually, that works quite well. So we here use two encoders. One is a hiding encoder, process only those unmasked tokens. So this is 5 by 5. Altogether, we have 25 tokens. And here we just have 1, 2, 3, 4, 5, 6, 7, 8. We just have 8 unmasked tokens. So we pass these unmasked tokens through a heavy encoder. And then we feed that together with the mask. So here the gray part means those tokens are masked. So we pass that through a light decoder. Okay, so we decode all the output tokens. So here are 25 from 8. And we try to reassemble them in the rasterizing order and try to recover the original image. So why do we need a highly versus light? Because the highly encoder deals with fewer tokens. Well, this light encoder can deal with more tokens. Actually, this method works quite well. For example, even if we mask a lot of components, like here, the clock becomes almost undistinguishable. But amazingly, this approach can still recover the clock, the bus, the dog, the lab, only with a few pixels. You can imagine there should be a limit we can mask away. We cannot mask away like 99% of the pixels, right? And it turned out the mask ratio will get a sweet spot at around 75%. So this is from 10%, this is 90%. So the sweet spot is roughly achieved at 75% mask ratio. Okay, you can still recover elevator quite well. Okay. So it has a pretty high mask ratio. Like BERT's mask ratio is only about 15%, but MAE can actually achieve 75%. What does that imply? Actually, that implies that image data has lower information density, okay? Very low information density, and more redundancy compared with language data, such that we can mask away more information and still we can recover the original information. So this is comparing the accuracy. Actually, these mass autoencoder works quite well, consistently higher accuracy than the baseline. Okay, so now let's switch gear to the third section and talk about generation, which is very new work done by our TA Hao Tian to talk about autoregressive image generation. So far, we all talk about something about discriminative models, right? Segmentation, detection, classification, right? So these are discriminative models. We try to predict like what is the class, for example, feeding in image patches, tokenize input image, and then pass it through a transformer, and then predict the final class. So those are discriminative models. Now we want to design generative models, can generate images, right? So autoregressive models can naturally generate tokens, right? So the natural thinking is, can we use the autoregressive transformer to generate visual tokens in a token in, token out manner? The input token could be the language, something we wanted to generate, and the output token would be the image token. Actually, such autoregressive image generation benefits multimodal language models. For example, Google Gemini's tech report hints that they are using the autoregressive model in individual generation, for example, with the important distinction that the models are multimodal from the beginning and can natively output images using discrete image tokens. So we designed this autoregressive generation, autoregressive short for AR, that can achieve even faster speed than diffusion models. So we are going to introduce diffusion in the next lecture, but here we'll give it a very quick hint. It has many time steps, try to predict the noise and try to denoise, right? To predict noise and then subtract the noise. And it requires many steps. And hard to require fewer number of steps and achieve much higher throughput, like 2 images per second compared with 0.2 images per second, much faster compared with here XCXL, Pixel Art, Sigma, Playground, SD, 3, etc. So how do we generate image tokens? What kind of order do we generate the image tokens? Okay, so in this paper, summarize 3 ways. The first way is just using the raster order, like 1, 2, 3, 4, 5, 6, 7, one by one. Okay? Each time we just generate one more token for one more patch in the rasterizing order. Okay? We can also use the random order. Okay? Next time we can generate this pixel, next time we can also generate another patch, right? Random order. But the problem here is that it generates each token at a time, which is memory bounded, as we learned during the quantization part. Single token generation, you need to go through all the weights, which is a lot. So we can also generate multiple tokens. Can we also generate multiple tokens, okay, at the same time? So rather than single token, can we generate multiple tokens at the same time? So those are 3 basic approaches. So what is different from language generation to image generation? For language, we have a fixed vocabulary, right? Like in English, we have like several tens of thousands English words, right? They are discrete. So that we can use the CE loss very easily to add the loss to supervise these discrete tokens. But images is different. Those pixels are actually continuous. Right? There's not such a vocabulary like 10,000 English words. There's not like 10,000 image patches. Right? So, but for which makes it difficult to supervise. Right? So an actual way to harmonize these 2 modalities is to use discrete image tokens, discrete image tokens, so that we can fit it into the same autoregressive infrastructure for large language model. Okay, we can supervise it by the same laws as language model. Okay, so previously we have an encoder, decoder. Now we added a new vector quantized encoder and vector quantized decoder together with a code book. Okay, so we turn those continuous image patches, these visual tokens, into discrete image tokens. Okay, we can decode it. Although there's a limited amount of tokens in the code book, we can have different mingling for these tokens such that we can decode them into various diverse images. This is highly related to the code book that we talk about during the quantization lecture. The difference is that previously we are quantizing individual weights or activations. Okay, so this is a scalar. We are doing a scalar quantization. Like these three values are all falling into this centroid, and we just store those centroid index. Okay, so now we are not quantizing individual weights, but a vector of pixels. Okay, so that's why we call it vector quantization. Compared with here, that's a scalar quantization. So we can do a vector quantization into the AI generation where each index may correspond to one of the indexes. For example, this vector, the closest color probably is right here, so we are storing index 2. Okay, and this color is different from any of them, but the closest one is V3, so we store vector 2. The blue is closest to this code, the entry in the code book, therefore we are storing entry 0, the index of 0. And you can see previously those contiguous vectors, now they are discretized. Okay, they are discretized, represented by integer values. So we can tell this is like a reborn of the deep compression from the closest centroid lookup to the closest vector lookup, and use the integer index to represent a vector instead of a single weight, so that we can generate those indexes, okay, which is discrete. And this work called VAR basically introduced a new order to generate the tokens. Okay? Remember, the rule of thumb is try to generate more tokens, not just one token. Generate more tokens at a time. So what it does is actually first generate one token, okay? Pull the entire image into a single token. And then a 2 by 2, 4 tokens. Okay, and then a 4 by 4, 16 tokens, 5 by 5, etc. Gradually increase the number of tokens to generate. You can also imagine this is like the big picture, very raw big picture, versus the last stage will be very high resolution details. Right? So from the big picture to the fine-grained details, from coarse-grained pixel to the fine-grained pixel. So that's the order where it's going to generate those tokens. And the interesting part is the tension mass. It's no longer the triangle shape. So what is the new shape? So imagine initially we generate just one token for the entire image, and then 2 by 2, 4 tokens, and then 3 by 3, 9 tokens. The mass will be like this, okay? Starting with 1, and then 4, and then 9. Okay? So in this way, when we are at this stage, like 3 by 3 token, we can generate 9 tokens at the same time. It's no longer memory bounded, like generate token by token. You have to fetch the entire weight for each token. It's purely memory bounded. Now it's no longer memory bounded, which is pretty hardware friendly. However, this is not perfect. You can tell the generated picture compared with the original reference. The eye looks different. The quality is not quite good. Right? So on top of that, we designed a new technique using a hybrid approach that can match perfectly with the original reference. And let's see more details here. So the discrete tokenizer inherently has its limitation. The images are contiguous. You force it to be discrete, right? So you can see the recover quality for the VAR model. The F is not quite well recovered. Similarly, right here, there is a lot of distortion in this area, versus heart to recover them quite well. So how should we build such a tokenizer? What's the limitation of the existing discrete tokenizer? So we introduced the capability to decode both the continuous and also the discrete tokens. Okay, so this is a continuous token. This is after the V2 quantizer, we get the discrete token. Okay, and if you skip the entire vector quantizer, just use the continuous token. Basically, the decoder becomes has the capability to decode continuous tokens. But in the training time, sometimes we sample directly from the continuous tokenizer, sometimes we sample the discrete tokenizer. So to make sure that they're in the same space, so that the same decoder can decode both the continuous token and also the discrete token. And at training time, we try to learn the residual token. Okay? The residual is the difference between the continuous and also the discrete token. You can imagine it's very difficult for us to learn those fine-grained details purely from these kind of discrete tokens. Okay? So we can offload the difficulty of learning those fine-grained details by a very small diffusion model. Okay? We call it residual diffusion. That model can be as small as like 30 to 40 million parameters compared with hundreds of millions of parameters. Just 30 or 40 million parameters. Very small residual diffusion model to learn the difference between the continuous token and discrete token. Okay? Just to learn the difference so that we can make this diffusion model super small and super fast. And let's try to see what are we trying to learn from the discrete token, which is basically the big picture, okay, versus the residual token. This is learned by a very small diffusion model. Those are the, we can hardly tell, but it's roughly the fine-grained details, versus if we combine them together, the discrete token versus the residual token together, it can give you very fine-grained detail. Like previously, you can see the eyes right here versus the eyes compared with the heart. This is the discrete only. This is the discrete plus the residual added a lot more fine-grained detail. Okay? So the discrete tokens are basically learning those big picture, versus the residual tokens are learning those fine details like the eyes, the hair, etc. And the natural question is how to efficiently model these discrete and the residual tokens at high resolution and guided by text prompt, not just the class prompt. Okay, so for class prompt, it is very easy. Like you just input a class index occupying a single token, like squirrel, and it's going to generate a squirrel. Okay, so we can animate the first text, so the first class index with the generated image tokens. So from 2 by 2 to this is 3 by 3. Sorry, this is 9 by 9. Since 3 by 3 we generate 9 tokens. Everything has to attend to each other. Okay, so this is purely using the discrete token. So from step 1 we get a 1 by 1. Step 2 we get 2 by 2, 3 by 3, all the way to much larger resolution. Adding a text prompt is pretty simple. We just pass through the text prompt through LLM, like beautiful cyborg with golden hair. We pass it through LLM, get a few text tokens. example showing 3 here, but we can have more. We just concatenate them together, and then it's going to generate the image. But this is actually not enough, because the generated, just using this discrete token, the generated images quality is not quite good. The generated image quality is not quite good. We need to also add this residual diffusion model, okay, to predict the difference between the original image versus the sum of the predicted token at different resolution, like 1 by 1, 2 by 2, 3 by 3, 4 by 4. We add them together. Okay? The task of the small diffusion model is to model the diff between the sum of the discrete tokens versus the final output. And this becomes quite easy, and only 30 or 40 million parameters is enough to complete this task, for the residual diffusion to learn these residual tokens. And finally, we add the residual tokens with the original discrete tokens to get the final output. And that's how we achieve such high fidelity visual generation here, and also achieve very high throughput. And this is comparing the hard versus the diffusion models. So the left column is hard, the prompt is a boy and a girl falling in love. This is hard. This is playground. This is pixel art. This is SDXL. These are all diffusion models. This is the second example. Full body shot, a French woman, photography, French streets. Compared with this is playground, pixel art, CXL. Third one is drone view of waves crashing against jagged cliffs in Big Sur. Very comparable accuracy. And the most exciting thing is hard can run at the interactive speed on a laptop. If you have a laptop with a 4090 mobile GPU, we can do image generation on it. So let's play the video. This is stream punk makeup in the style of V-ray tracing. Okay. It's almost instant. Just click the button and then we can run the model. This is an astronaut riding a horse, the classic demo. We can also do a dog that has been meditating all the time. A neon holography crystal cat or crystal dog. Just take 1 second. And this is everything is local. There's no internet connected to the laptop here. An astronaut in a huge GPU cluster. Okay, if you're interested to play with more demos, welcome to try. Just go to heart.mit.edu. There are more examples. We can also try New England fall with the river, with the house, and then you can immediately generate new images. Or we can try some default new holographic crystal cat and run it. It will generate instantly. Okay, go back to the slide. So let's summarize today's lecture. We basically started with the basics of vision transformer. Everything can be tokenized, not only language, but also images can be tokenized. So we can have token in and token out. And the basic architecture of VIT grows, the computation grows quadratically with the resolution. So how do we make it more efficient? We can first try the window attention. So only everything is constrained locally within that window. We can also use linear attention using efficient VIT. I use sparse attention, not all the windows need to be attending to each other. And then we talk about how do we deal with the data efficiency of VIT, basically not requiring a lot of well-labeled data, but using self-supervised learning, including contrastive learning and also masked image modeling. And finally, we talk about not only the understanding or descriptive model, but also the generative model. How do we use this token in, token out approach combined with a very lightweighted diffusion model to do autoregressive, to apply this hybrid autoregressive transformer hard to do image generation. So in the next lecture, we'll introduce diffusion models for image generation. So all the code for EfficientML.ai and HART is open sourced. So if you're interested in continue developing HART or use HART as a tool for other applications, you're welcome to talk to us. And the TA is Hao Tian, he's the author of this paper. Feel free to try it out. And we will release the grading for lab 2 and 3 by this weekend, by this Sunday. So if you have any questions, feel free to talk to us. And it's time to get started to think about the final projects. We already released many project ideas. Some of them is very hardcore, some of them is related to application. We don't want to constrain your imagination, so feel free to select the one you are most interested in, and we are always here to help during the office hour. All right, that's all for today's lecture. Happy Halloween.